Hi everyone. In this section, we'll look at total internal reflection and dispersion. I want to start with an example to introduce total internal reflection. Example 5, consider a beam of light that originates in water and propagates into air. Calculate the angle of reflection and the angle of refraction if theta I is 20 degrees, 30 degrees, 40 degrees, and 50 degrees. Okay, so it looks like this. We have an object or something in water emitting light, and then it's passing through to air. It doesn't matter which side you draw these on, by the way. Maybe it makes sense to put water on the bottom physically, but it doesn't matter. So 1 is water and 2 is air. And then I've made this chart, so for each of the angles, we can fill in the angle of reflection and refraction. So we have 20 degrees, 30, 40, and 50. All right, so right away we know that the angle of reflection for each of these cases will be equal to the angle of incidence. So at the boundary, part of the wave is reflected and part is refracted. The reflected part is also at the incident angle. So we can fill all of those in, 20, 30, 40, and 50. Okay, then we need to calculate the angle of refraction using Snell's law. Let's do the 20-degree angle. So we'll have N1 sine theta 1 equals N2 sine theta 2. So theta 2 is sine inverse 1.33 sine 20 over 1. And for 20 degrees, that gives me 27 degrees. Okay, I won't write them all out, but you can repeat this same calculation for the next box here. So for 30 degrees, just replace 30 degrees here, and then we calculate again, and we get 41.7. And then again, 40 degrees here, using that for theta 1, gives me 58.7. Okay, and if you haven't yet, now try using 50 here. So at an angle of incidence of 50 degrees, we plug this in, and what happens is we get an error. So this will give us a math error. So I'm going to write not applicable here. And the reason we're getting a math error is because the argument then of this sine function, 1.33 sine 50 over 1, is actually greater than 1, and that's not possible for sine, so there is no solution. And physically, this does have a physical meaning. It means that there's no refraction at this point. So all of the light is being reflected back into the medium, back into the water. Generally, when light encounters a boundary between two media, we know that part of the light is refracted and part of the light is reflected. In this case, where we have light traveling from a medium of higher index, such as water, to a medium of lower index, like air, we can have total internal reflection. So if we look at this, as light is incident at a specific angle, it will transmit into the air and refract away from the normal, as we'd expect. Then, as this incident angle is increased, it eventually reaches a specific angle called the critical angle. When the incident angle is equal to the critical angle, the refracted portion of the light will refract along the boundary between the two media. So this has an angle of refraction of 90 degrees. That's kind of the limiting point. After that point, for any incident angle greater than the critical angle, like this case, 100% of the light is reflected back into the first medium. And this is perfect reflection. It's even better than reflection from a plane mirror. All of the light is reflected and there's no light that is refracted. And again, this only happens when light travels from a medium that's higher index to lower index. Okay, so I've written out the math for this. Again, the critical angle is the incident angle for which the light is refracted along the boundary. So the incident angle that corresponds to a refracted angle of 90 degrees. So we can find an equation for this just by using Snell's law. So in order to find the critical angle, we want to replace theta 1 with theta c and theta 2 with 90. And then sine of 90 is 1. So we get this nice equation, sine theta c equals n2 over n1. And you'll notice this can only work if n1 is greater than n2. So total internal reflection occurs when, after this critical angle, as the the incident angle is increased, we have 100% of the light reflected. That's total internal reflection. And for it to happen, we need n1 greater than n2, and we need theta 1, the incident angle, to be greater than the critical angle. So this only happens in with these two criteria. If we have light going from something that's lower index to higher index, like air to water, total internal reflection will not occur. At every incident angle, part of the light will be refracted and part of the light will be reflected. So at all of those incident angles, we still have refraction occurring. Okay, so in the previous example, let's just check what the critical angle is for water to air. So we would do theta c equals sine inverse of n2 over n1. So that's going to be 1 over 1.33, which gives 48.6 degrees. So that's why we were seeing refraction with an angle of incidence of 40 degrees, but once we passed 48.6 degrees, instead we have total internal reflection. Okay, now let's look at dispersion. So far we've considered the index of refraction to be constant for light in a specific type of medium. So we do know that the index depends on the type of medium, which is still true, but it also depends slightly on wavelength. White light contains all colors of light, and each color of light has a different wavelength. And then there is this slight variation of the index with the wavelength. It's inversely proportional, so as n decreases, as lambda increases. And dispersion is this effect that occurs because of this. It is the variation of index of refraction with wavelength, which results in the separation of colors of light due to refraction. So this means that violet light, which has a shorter wavelength, would refract more than red light in the same medium. And this is what leads to prisms separating colors of white light. The effect is actually magnified in a prism because there's refraction at both boundaries, and we'll look at that in the example. Example 6, the index of refraction for violet light in silica flint glass is 1.66, and that for red light is 1.62. What is the angular dispersion of visible light passing through a prism of apex angle 60 degrees if the angle of incidence is 50 degrees? Okay, so let's have a look here. I've drawn this out. It's a bit exaggerated, but basically what happens is we have the white light coming in here at 50 degrees, and then each of red and violet light refracts different amounts, and then travels to the other side, and then we see again this refraction being amplified at the second boundary. So we want to apply Snell's law and trace each light ray through the prism separately. So let's start with red light. For red, we have n is 1.62. And first we're going to need Snell's law at this first surface. So n1 sine theta 1 equals n2 sine theta 2. We get theta 2 equals sine inverse 1 sine 50 over 1.62. So 28.22 degrees. Okay, now we want to apply Snell's law here at this second surface for the red light. And so I'm going to need this angle in here. So this angle I've called theta 2. Let's call this angle over here theta 3. So we want to find theta 3. What we can do is look at this triangle at the top and then use a relationship here, use the relationship that all the angles in the triangle have to add to 180 to find that angle. So we'll have 180 degrees minus the apex angle. The apex angle is at the top of the prism here. And then minus this angle here. This angle is 90 minus the one we found, so 90 minus theta 2. And then also minus this angle. So this angle is going to be 90 minus theta 3. This equals 0. So notice we have 180 minus 90 minus 90. So, and then if we solve for theta 3, we get theta 3 equals theta apex minus theta 2. So we can take our apex angle, which in this case is 60 degrees, and subtract 28.22 to find theta 3. Okay, so let's do that. We get theta 3 equals 60 minus 28.22, so 31.78. And now that's theta 3, or our angle of incidence at the second boundary. And the last step is to apply Snell's law again there. So now I'm going to have, do we want to call it N3? It's still the index in the glass or in the prism. So N3 sine theta 3 equals N4 sine theta 4. And we end up with theta 4 equal to sine inverse 1.62 sine 31.78 over 1 for air, since it's going back to air. That's our N4. And then our final angle of refraction out of the prism for red light is 58.56 degrees. So that angle we found, just to flip back up, is here, theta 4. Okay, so I'm going to just repeat this for violet light. So I've left space beside because we essentially want to do all of the same steps again. So let's do violet light over here. For violet, we have 1.66. So first, finding theta 2 inside the prism, that will be sine inverse 1 sine 50 over 1.66. Same step as here, which gives me 27.48. Okay, and then we want to find theta 3 for violet, which will be 60 minus 27.48. So 32.52. Okay, and lastly, Snell's law again to find theta 4, sine inverse 1.66 sine 32.52 over 1. Okay, which is 63.18. And then we're asked for the angular dispersion. This will be the difference in the two exit angles from the prism. So the amount of separation, or the angular separation of the two colors. So this is 63.18 minus 58.56. And that's 4.62 degrees, which is quite significant, and definitely we're able to notice that angular separation and see different colors. Okay, so I just wanted to show you that we did end up with the violet light refracting more in a sense than the red light, meaning that it refracts at a smaller angle here, or it refracts more towards the normal than the red light. So it does look like this in my diagram roughly. This isn't to scale, of course, where we have the violet closer to the normal here and hitting the prism at a lower position on the exit side, or the second surface. I'll just put all of that up for another second. There. Total internal reflection and dispersion have some very interesting examples. So first, an example you might have thought of for dispersion is rainbows. So we see the colors of white light separated in the sky because of their dispersion or refraction within water droplets. I've drawn an example here of a water droplet. So white light would enter the droplet, and then it separates the colors, since they all have a slightly different index of refraction in the water, into the full spectrum of colors of the rainbow. Now we see these as bands because the light will then be directed at different angles, and only certain rays will enter our eye, and it depends on the height of the droplet. So water droplets at different heights will refract different colors that reach our eye, and we end up seeing these bands of different colors in the sky. Okay, an example of total internal reflection, we'll have two. One is binoculars. Binoculars actually use total internal reflection in prisms in order to redirect light so that light would enter the binoculars and then different prisms and setups would allow that light to be directed into the eyepiece. And usually it's a glass with a low critical angle. So for example, n is 1.52, which gives a critical angle of 41.1 degrees. And then if we have this prism here, this would mean that the light here is intersecting this surface at 45 degrees and then refracting straight out this other side of the prism. So, and that's used instead of mirrors because this has even higher percentage of reflection than a plane mirror, as I said before. Okay, and then the last one is fiber optics, which are used to transmit light in computers and telecommunications. So this would be generally a glass fiber, and light would enter the fiber, and then at every boundary as it passes through, it experiences total internal reflection so that the highest amount of light can be transmitted all the way through to the end of the cable.